Modern industrial food processing operates at extreme volume and velocity. High-speed automated lines and human operators handle millions of pounds of raw organic material daily, requiring specialized protective barriers to maintain sanitation. Those barriers are almost exclusively synthetic elastomers, gloves made from nitrile, latex, or vinyl. The constant friction between these synthetic polymers and organic matter creates a highly efficient vector for chemical transfer. Under continuous physical stress, materials like nitrile and vinyl can invisibly leach chemical monomers, plasticizers, and structural stabilizers directly into the food matrix during handling. This risk of invisible chemical migration is the precise reason global testing protocols dictate which materials are allowed in processing facilities. A glove cannot touch the food supply until its chemical stability is proven. That proof exists as a single legal artifact, the Declaration of Compliance. This document mathematically confirms that a specific glove material prevents hazardous substance transfer and prevents sensory alterations to the taste, odor, or chemical composition of the food. To understand how this document is assembled, we have to reverse engineer it. The certification relies on a rigorous sequence of targeted chemical simulants, strictly enforced extraction limits, and precise physical barrier tests. Food safe is not an inherent trait of a polymer. It is a highly conditional, heavily quantified laboratory state that must accurately reflect the exact physical and chemical environment of the factory floor. Establishing a repeatable chemical baseline requires standardizing the test environment. Real foods are chemically chaotic and highly variable, making them useless for strict laboratory extractions. The regulatory solution is to remove actual food from the process. Laboratories replace it with standardized chemical simulants engineered to mimic the extraction properties of different food categories. Laboratories use these simulants to perform controlled extractions under accelerated, worst-case exposure environments, ensuring the material holds up to extreme real-world processing demands. This matrix links distinct food types to their designated laboratory simulants. We start with simulant A, a 10% ethanol solution used to model water-based aqueous foods. Right below it is simulant B, a 3% acetic acid solution designed to mimic highly acidic foods with a pH below 4.5. Operations handling alcohol require simulant C, a stronger 20% ethanol solution that aggressively tests the polymer's resistance to alcoholic food environments. Finally, we have simulants D1 and D2, comprised of vegetable oil and 50% ethanol. These are specifically engineered to extract chemicals into fatty, oily, and dairy products. Standard exposure protocols execute these tests at 40 degrees Celsius for anywhere from 30 minutes up to 2 hours, depending on the industrial contact times expected in the target facility. The validity of a compliance document depends entirely on selecting the correct simulant. Approving a glove with a water-based simulant when the factory line processes fatty meats renders the safety certification mathematically useless. In the United States, rubber and elastomer articles intended for repeated food contact must pass strict extraction testing mandated by the Food and Drug Administration under Regulation 21 CFR 177.2600. This split-screen visualization plots the FDA's dual testing mandate. Manufacturers must measure the total mass of extracted chemicals in milligrams per square inch, running separate tests for aqueous extraction and fatty food extraction. The aqueous extraction protocol subjects the glove to distilled water at extreme reflux temperatures. The mathematical limits here are strict. The total chemical mass pulled from the glove must not exceed 20 milligrams per square inch during the first 7 hours of extraction, and no more than a single milligram per square inch over a subsequent 2-hour test. The fatty food protocol replaces water with N-hexane, a highly potent hydrocarbon solvent that perfectly simulates constant contact with oils and fats. The allowance for fatty extractions is drastically different.
The limit expands to 175 milligrams per square inch during the first 7 hours, dropping to 4 milligrams per square inch in the final 2-hour window. The gap between 20 milligrams and 175 milligrams exists because hydrocarbon-based fatty foods naturally dissolve and pull significantly more chemical mass from elastomer structures than water ever could. By setting these specific milligram limits, the FDA establishes the definitive legal boundary that prevents toxic chemical accumulation across the American food supply chain. Across the Atlantic, the European Union regulates chemical threats through Regulation 10/2011. While the objective is identical, the EU framework approaches the math through standardized migration testing. European laboratories follow the EN 1186 testing protocols, which govern exactly how chemical transfer is measured. The primary metric in this system is the overall migration limit, or OML. In this 1 decimeter squared grid, we measure the OML as the total aggregate weight of all non-volatile substances transferred from the glove into the simulated environment. Under EU law, the combined mass of these migrating substances must strictly not exceed 10 milligrams per square decimeter of glove surface. But an aggregate weight cannot catch hypertoxic trace elements. For that, the EU enforces the Specific Migration Limit, or SML, acting as a highly targeted secondary safety net. The SML measures the isolated release of restricted substances, enforcing distinct microsealings for highly sensitive elements like heavy metals, heavy monomers, and plasticizers. This creates a two-tiered chemical defense. The broad OML ensures the glove will not degrade the sensory properties or overall makeup of the food, while the targeted SML prevents trace elemental poisoning. Chemical compliance metrics are completely voided if the physical structure of the elastomer fails.
A microscopic tear bypasses all migration limits. To prove physical integrity, gloves undergo the EN 455 water leak testing standard. The material is pressurized with fluid to detect microscopic pinholes that would allow biological fluids and sweat to cross from human skin directly into the food matrix. The failure rate determines the acceptable quality level, or AQL. Any batch certified for food handling must meet an AQL of 1.5 or lower to pass the physical barrier test. Physical contamination extends to manufacturing residues as well. Any glove certified as powder-free must prove that residual powder remains strictly below 2 milligrams per glove. For gloves destined for raw meat processing and ready-to-eat foods, manufacturers must also execute biological safety screening, ensuring the surface is entirely free of active pathogens like Salmonella and E. coli. Without an AQL of 1.5 and a verified pathogen-free surface, the entire chemical testing matrix is compromised by direct physical exposure. Quality assurance teams do not run these tests themselves. Their objective is to validate that the manufacturer has executed the protocols correctly, a verification that brings us back to the final declaration of compliance. This master document synthesizes the isolated laboratory data. It explicitly lists the simulant types utilized, logs the FDA extraction milligrams and EU migration weights, and confirms the final physical AQL scores. The critical review phase is verifying simulant alignment. The QA team must ensure that the specific simulants listed on the document perfectly match the actual processing environment of their factory floor. At the bottom of the declaration lies the ultimate operational safety net: batch-level traceability. Under good manufacturing practices, these batch codes allow investigators to rapidly identify, trace, and isolate specific manufacturing runs if a post-market contamination event triggers a recall. A food safe certification is a living operational contract. It is a rigorous alignment of polymer chemistry, laboratory simulation, and strictly enforced legal thresholds, all working together to protect the global supply chain. In industrial food processing, safety is never assumed. It is meticulously extracted, measured, and documented.